The Chinese Mars orbiter captured a rare glimpse of 3I Atlas during a period when NASA had not released new observations, and the differences drew attention. The Chinese images revealed a much more active object than previously shown. The coma was brighter, more extensive, and accompanied by a sudden increase in luminosity that did not appear in NASA's public data. The encounter occurred on October 3rd, when the interstellar visitor passed closest to Mars. During this interval, Chinese records showed a clear transformation. The coma expanded to about 400,000 kilometers in diameter, approximately 3 times the size of Earth, with more defined edges and an unusual brightness directed towards the Sun, something unprecedented in previous observations. There was also a change in the tail. While NASA data indicated a straight tail away from the Sun, the new images showed a slight curvature towards it, a sign that new jets of material have opened up on the object's surface. This confirmed that 3I Atlas is active and behaving like a comet. The internal distribution of the dust also changed. The brightness pattern suggested the presence of larger grains, indicating that deeper layers broke apart due to solar heating, unlike the thinner, more homogeneous cloud observed before. Finally, spectroscopic analyses pointed to a stronger carbon dioxide signature than that detected in NASA measurements prior to the gap, reinforcing the idea of sudden and intense activity in this ancient interstellar traveler. Such an increase points to the warming of deeper ice and its release into space. This type of release can occur rapidly when sunlight reaches a part of the surface that was previously protected. Each of these changes appeared within the short time frame that only one country recorded. The altered coma, the curved tail, the larger dust grains, and the more intense carbon dioxide signal belong to this part of the event that NASA never recorded. The gas plume around the object is composed mostly of carbon dioxide, about 95% by mass, based on space telescope data. That's why the new images are so important. They document the moment when the object reacted to sunlight in a way that didn't appear in Western data and reveal the first clear sign of a rapid change in the behavior of 3I Atlas. We have a major update, a huge update on our favorite interstellar object. It may be the biggest update ever seen in the solar system. What NASA released. NASA released several images of 3I Atlas before the shutdown period, and these images showed a stable object with a thin coma, a straight tail, and no sharp increase in brightness. This comet is really interesting because it has a tail formed by solar radiation, but it also has a forward-facing tail. Nothing in these images suggested that the object was entering a more active phase. After this update, the flow of new material was interrupted. The gap that followed is exactly the period that China observed in its entirety. NASA's public archive does not contain raw images of the perihelion passage. Perihelion is the point in a comet's orbit where it passes closest to the Sun. At this point, solar radiation heats the surface and vaporizes the ice, making perihelion the most active and valuable phase for observation. These materials are vaporized by sunlight before they even have a chance to reorganize and reappear. NASA has not published brightness curves for these hours, nor has it provided new dust readings or any updates on the tail's structure. The subsequent disclosure only occurred after the object had already moved away from its most active zone, meaning that the changes seen in the new images from China do not appear in any public NASA records. It is not possible to accurately determine the size of the core, partly due to the object's dimensions, but also due to its activity. NASA described this as a routine interruption for instrument calibration, a standard practice at astronomical facilities. The problem was the unfortunate timing, as this maintenance coincided with perihelion, when continuous observation is most useful for understanding how an object reacts to solar heat. NASA also did not address the clear differences between its latest sequence and the new images released by China. NASA showed a thin coma, while China recorded a larger and brighter one. NASA showed a straight tail, while China documented a slight curvature. NASA detected a weak carbon dioxide signal, while China measured a more intense signal. These differences remain unresolved because NASA has not published equivalent observations from the same period. NASA has not disputed the Chinese measurements, nor has it released alternative images showing a similar level of activity. China recorded the hours that do not appear in NASA's sequence, and these hours contain the changes that defined the object's appearance in the new images. Now we have a better idea of this object's orbit. It could be a completely new, unknown, and potentially hazardous object. Until NASA provides data from the same time frame, both records will continue to show two different sides of the same event. The missing frames are also important because perihelion is the only point in the orbit where a comet reveals its internal structure. As sunlight reaches deeper layers, different types of ice vaporize at distinct temperatures, and each leaves a clear chemical signature. Without continuous observations throughout this period, scientists lose the ability to track how the surface layers flake off and how the chemical composition changes over time. The object is moving along a very specific trajectory. Images from China captured these changes, while NASA's sequence ended before the reactions began. Another important detail is the timing of the dust release. The size and speed of the ejected grains help researchers estimate how cohesive the surface material is. This provides clues as to whether the comet formed in a cooler or warmer region of its parent star system. Readings from China documented the beginning of this release, offering scientists the only point in the timeline that shows how the surface responded to the temperature increase. NASA's data, which stops before the active phase, cannot provide this initial reference point. By chronologically aligning the two datasets, the transformation becomes clear. The comet observed by NASA before perihelion and the comet observed by China during perihelion are the same object at different stages of solar activity. This is normal for icy bodies that pass close to the Sun. The outer layers remain inactive until sunlight reaches the deeper ice. When this ice warms, the entire surface can change in a matter of hours. NASA recorded the calm phase. China recorded the moment the surface began to react. The first major change appears in the coma. The latest NASA images showed a thin halo that dissipated smoothly at the edges. China captured a much wider halo with defined boundaries and more intense light throughout the cloud. This expansion means that gas and dust were released from the surface during the interval that NASA did not observe. An interstellar visitor is rewriting the rules, while NASA remains silent, still withholding crucial information. Near perihelion, heat can spread through fissures or pores in the ice and reach deeper pockets. When this happens, the ice erupts, carrying material that forms a brighter coma. The structure of the tail also changed during this period. NASA recorded a straight tail, clearly pointing away from the Sun. China documented a slight curve towards the Sun, suggesting that the dust was pushed in a new direction. This can occur when a jet stream on the surface opens at a different angle than the previous stream. Even a small jet stream can alter the shape of its tail because the dust is light and travels great distances once it leaves the surface. A very dense and massive cloud of gas and dust forms, pushed away from the Sun by solar radiation. Changes of this type are in line with the activity observed in many other comets when they reach perihelion. Brightness measurements show the strongest shift. NASA detected a slow and steady increase in luminosity. China measured a sudden increase that occurred over a short period of time. A jump like this can happen when deeper ice breaks off and releases gas in a single event. NASA's sequence ends before that point, which is why the abrupt increase only appears on the Chinese curve. This type of brightness intensification has clear scientific examples. Comet 17P Holmes had its brightness increased by a factor of 500,000 in about 42 hours in October 2007, when subsurface ice vaporized all at once. The change recorded in 3I Atlas is much smaller, but the pattern is familiar. Comets often exhibit their most intense response at their closest point to the Sun, and this response can occur rapidly. The composition of the dust adds another layer to the change. NASA detected mostly fine particles, which come from the outermost layer of the surface. China measured larger grains mixed throughout the coma, indicating that deeper layers have been exposed. Larger grains form when material breaks away from stronger bonds below the surface. These grains do not travel great distances unless a fresh jet of water opens up. Their presence confirms that heating has reached a new depth during the absent hours. Chinese measurements have also improved the accuracy of the comet's trajectory. Additional measurements taken during the active phase reduced positional uncertainty by about 30%. When the coma expands and jets form, small forces act on the nucleus. These forces can slightly alter the path. By capturing the moment when these forces were most intense, China added information that NASA did not possess. None of these changes point to a conflict between the two data sets. They describe the same comet at two different times. NASA observed the stable phase before perihelion. China observed the active phase during its closest passage to the Sun. The differences stem from the timing of the observations, and the missing hours contain the reactions that explain why the comet appeared so different in each recording. What does this mean for the 3I Atlas now? Observations at perihelion show that 3I Atlas reacted more strongly to solar heating than initial data suggested. Before perihelion, the comet appeared calm and predictable. During perihelion, it behaved like an object under sudden stress. This brief interval reshaped the coma, curved the tail, and increased the brightness in ways NASA never recorded. The event transforms a silent visitor into a much more dynamic object. Only in the last decade have we begun to find interstellar objects. It's a new frontier. We don't know if we've been visited before. The wider and brighter coma in the images from China is the clearest sign of this change. A coma forms when ice turns to gas and carries dust away from the surface. In pre-perihelion images, the cloud remained compact and tenuous. During the active phase, it expanded to a much larger scale than before. This type of growth means that deeper layers of ice have begun to vaporize. The surface not only warmed up, but parts of it opened up and released stored material. Changes in grain size within the coma support this idea. NASA data indicated mostly fine dust. Fine grains generally come from loose material in the outer crust. China measured larger grains mixed throughout the coma. Larger grains are heavier and more difficult to lift. Their presence indicates that deeper, more tightly bound material has detached. This suggests that the core has a layered structure, with ancient compact ice beneath a softer layer. The change in the tail adds another clue about the geometry of this activity. Tails form when sunlight and solar wind drag dust away from the sun. NASA recorded a straight tail following this expected path. China observed a slight curve towards the Sun. The article mentions the interstellar object 3I Atlas as alien technology. This curvature suggests that a jet stream on the surface pushed the dust out of the main stream. Even a small jet stream can tilt its tail if it operates long enough. The angle seen in the images helps to indicate the region where the jet stream formed. Brightness measurements show that this was not a slow and gradual change. NASA recorded a steady increase in brightness as the comet approached the Sun. China measured a sharp jump within a very short interval. This pattern corresponds to a sudden release event. A sealed pocket of ice ruptures, gas escapes rapidly, and the coma suddenly brightens. After that, the brightness returns to a more gradual increase. The NASA sequence ended before this jump began, so the peak only appears in the Chinese curve. The strongest carbon dioxide signal in the Chinese spectra completes the picture. Carbon dioxide ice is more volatile than water ice at close range, but it is generally buried deeper beneath the surface. When sunlight finally reaches these buried layers, the gas escapes and leaves a distinct chemical signature. NASA's weaker signal indicates that these layers remained sealed during its observation window. China's stronger signal shows that the buried ices were finally exposed during the missing hours. China's updated orbital solution reveals the mechanical effect of these releases. When gas flows in one direction, it gives a small push to the nucleus. This non-gravitational force can alter the trajectory over time. The 3I Atlas offers scientists a rare chance to study something from outside our solar system. Additional measurements from China during its active phase have reduced the uncertainty in its orbit. The range of possible future positions has been narrowed. This helps confirm that the burst of activity has not turned 3I Atlas into a threat, while also showing that its trajectory is not purely passive. For comet researchers, these observations are a rare opportunity to test models of interstellar bodies. 3I Atlas will not return in a closed orbit. It came in from interstellar space and will leave again. Each change in brightness, tail shape, and chemical composition reveals something about the environment in which it formed. The strongest signal of carbon dioxide suggests a cold origin, rich in volatile ices. The heavier dust indicates a long history of slow compaction within the core. The sudden explosion near perihelion shows that these layers can remain stable for millions of years and still react violently when heated. This event also highlights how much it depends on complete coverage. With only NASA data, astronomers would see a mild-mannered comet without major events. With the perihelion images captured by China, the same object becomes a classic case of rapid activation. This difference changes how future interstellar visitors should be programmed for study. This shows that observatories need dense monitoring around perihelion and shorter maintenance windows when rare objects reach peak heating. Currently, 3I Atlas is moving away from the Sun and cooling. The coma will slowly decrease as gas production declines. The tail will thin out and extend in a more regular line. Astronomers have planned follow-up observations with ground-based telescopes in both hemispheres. They want to measure the speed at which the coma contracts, how long any jets remain active, and whether the chemical composition returns to its pre-perihelion state. Later on, all these stages will be combined into a single continuous record. The calm approach observed by NASA, the abrupt explosion captured by China, and the dissipating trail that follows will form a complete timeline. This timeline shows how an interstellar object reacts to a star around which it did not form. In this sense, 3I Atlas is not just a comet. It is also a sample of the building blocks of another system, and the perihelion images reveal that these blocks are much more reactive than initially appeared. Why does this matter? If the object were technological, it would maneuver in some way, emit some signal, or have artificial lights. The new images from China fill in the only missing part of the entire observational record of 3I Atlas. NASA's sequence ends before the object becomes active. China's sequence begins during this active phase. When the images are arranged sequentially, the missing hours become the key to understanding why the object presented such different appearances. The new images, obtained only by China, reveal changes that did not appear in Western releases: expansion of the coma, alteration of the tail, a more intense signal of carbon dioxide, and a sudden increase in brightness. All of this occurred during the interval in which the comet transitioned from a calm to an active state, when sunlight reached deeper layers of ice and dust. These observations also allowed for refining the object's trajectory. Additional data collected during the period of greatest heating reduced uncertainties about its path and confirmed that the recorded activity was real, not a measurement error. The difference between the datasets is simple. NASA observed the comet before its response to the Sun. China, during that response. The new images fill the gap that explained the change in its appearance and indicate nothing more than natural comet behavior. They show how an interstellar object reacts to solar heating and why this moment is scientifically valuable, since these bodies carry chemical material from other star systems. As 3I Atlas moves away from the Sun, activity tends to decrease, making this brief burst, recorded only in this window, the most complete record of its most active state and the missing element to understanding its behavior at the peak of solar heating.